Hi, good morning to all of you. Good evening to all of you. As you know that I'm a research scholar in ISC and I'm your TA for this course of Introduction to Photonics. We have already done 7 classes in which we learned about the basics of photonics, that is about the dispersion of light, the properties of light, about the electromagnetic optics and optical amplifiers, optical fibers, lasers. Today we'll be talking about some semiconductor light sources, and the next week we'll be talking about semiconductor detectors. So before moving on to semiconductor light sources and detectors, what do we have to do? Okay, so before moving on, we have to focus on what is the meaning of semiconductors and about the band structure. How is it different from a metal or an insulator, and why is it called a semiconductor? So based on that, this is my first. Yeah. So I was saying that before moving on to the semiconductor, so light sources and detectors, we need to know about the basics of semiconductors. So how do we differentiate a semiconductor from an insulator and a conductor, and why is it called a semiconductor? So based on that, this is my first question. The first question is, you have to identify in this diagram, this is a band diagram of different materials: insulator, conductor, semiconductor. So which one is an insulator, which one is a conductor, and which one is a semiconductor? So can you please answer this question? Here I have a diagram where the conduction band and the valence band are overlapping, okay? And then I have another diagram, that is B, of a conduction band and valence band having a band gap of 1.1 electron volts. Then again, I have a conduction band and a valence band, but these two are separated by a very large energy gap, and this energy gap is around 6 electron volts. So can you please answer this question, that which is the band diagram of a conductor, semiconductor and insulator out of the three?
Option A is a conductor,
Okay.
option B is a semiconductor, and option C is an insulator because there is
All
a
right.
more gap, energy gap.
Right. Semiconductor, and this is an insulator. Okay. So from the band picture, we can differentiate between a conductor, semiconductor, and insulator. So why is it called a semiconductor? We say there's a conductor, there's an insulator, there's another material called semiconductor. Why do you call it a semiconductor? Do you know the answer to this? You can answer. You can answer. Why is it called a semiconductor? Okay, I'll tell you. Because the conduction of this material, this semiconductor, lies in between that of a conductor and an insulator. So an insulator is an insulator at room temperature, even at T is equal to 0 Kelvin. A conductor becomes a conductor at room temperature and also at T 0 Kelvin. But about a semiconductor, at T is equal to 0 Kelvin, it is an insulator. Okay? So, the presence of free electrons in a material defines it as a conductor, semiconductor, or an insulator. In a conductor, there is an abundance of free electrons. That is, electrons are already in the conduction band. Okay, and so we have a flow of like if we give a bias to this material, there will be a large flow of current. That is, the rate of flow of charge will be quite large because the electrons are already free to move in the conduction band, and there is no forbidden gap for a conductor. So the conduction band and the valence band are partially filled and they overlap. Okay, but for an insulator, there is a slight band gap that is in the range of 1.1 electron volts, like around, for silicon germanium, see, it's around 1.1 electron volts. So it moves like that, and up till I think it's up to 2 electron volts. We can see the range, in what range the band gap of a semiconductor lies. So there in this small range, at T is equal to 0, it's an insulator because all the electrons are lying in the valence band. All the electrons are lying in the valence band. So at some temperature, say at T is equal to some temperature, say the room temperature, the electrons gain some thermal energy, and what they do, they can the energy is sufficient enough so that they can jump this band gap, they can cover this gap of, or the energy is greater than 1.1 electron volt, that the electrons can go from a conduction band to a valence band, and hence it becomes a conductor at that temperature. That's why we call it a semiconductor, because its conductivity lies in between that of an insulator and conductor. And an insulator is an insulator because it has a very large band gap, and we need to provide it very large energy, so that I can have free electrons in the conduction band. Okay, so that's why it's an insulator, because of the lack of free electrons. It's an insulator. So it's an insulator. So now I would be saying that yeah, can you give an example of a conductor, semiconductor, and insulator? Chemist, can you give an example of a conductor, semiconductor, and insulator?
I'm country silicon, germanium,
Yeah.
and
Conductor, all metals. Conductor, example, I would say
conductor,
copper.
iron,
Copper.
copper,
Semiconductor is silicon, germanium. Some compound materials are also
gallium arsenide,
semiconductors. Yeah, gallium arsenide, indium gallium
yes,
arsenide,
ma'am.
insulator,
Insulator, ma'am, wood or
diamond,
plastic, diamond, yes, ma'am.
diamond. All these are insulator. Okay, so this is the whole idea of segregating our materials into conductor, insulator, and semiconductor, and that is done based upon the availability of free carriers and the band gap between the conduction band and valence band. And one good thing about the semiconductor, like in a conductor, the conduction is wholly because of the electrons, but in a semiconductor, conduction, there are two types of carriers in this. There are two types of carriers, electrons and holes. So what are holes? Here, when an electron jumps from valence band to conduction band, it leaves behind holes. Okay, so what are holes? Can Camels answer? Holes are basically just an absence of electrons, and it moves in a direction which is opposite to that of an electron. So suppose an electron is here, it gains energy, jumps to the valence band. So what will happen? It jumps to the valence band, then here it will leave behind a hole. So electrons, if it moves in this direction, holes will move in this direction. You got it? So if an electron moves in this direction, the hole will move in this direction. You got it? You got the whole idea? It's clear? I hope it's clear. So let's move on to our next question. What's the next question about? Okay, can you see the diagram?
Yes,
Now
ma'am.
here, what do you think? What is this? What device is this? I'll tell you what device it is. It is a PN
PN junction.
junction diode. Okay, so this PN junction diode is important to understand if you want to understand the light sources. So basically the light sources are LEDs. LED means a light emitting diode. To understand the working of an LED and how we get light from it, we need to understand the working of a PN junction diode. So please tell me that in this PN junction diode, what are the regions 1, 2, and 3?
One is P-type semiconductor, three is N-type semiconductor, two is depletion layer.
Correct. So here, okay, I didn't give one thing. I'm sorry for that. These particles are holes and these particles are electrons. And this thing, it has already been given a negative ion and positive ion. So we have now differentiated our materials into semiconductor, insulator and conductor. In semiconductor, we said that there are two types of carriers, electrons and holes. Okay, so the good thing about a semiconductor is you can increase its conductivity by increasing the number of carriers. Now, how do you increase its conductivity? By increasing the number of carriers. So, increase conductivity for a semiconductor by increasing number of carriers. Number of carriers. Now, how do you increase the number of carriers? Number of carriers, So how do you increase the number of carriers? Number of carriers are increased by doping. By doping it with an appropriate material. So if you dope a semiconductor with some impurity, then we get an excess of holes. If you dope it semiconductor with some other kind of impurities, then we get excess of electrons. Now my question to you is, what kind of impurity should be used for getting an excess of holes, and what kind of impurity should be used to get an excess of electrons in a semiconductor? This is an easy question, you can answer.
Bivalent elements for p-type, pentavalent elements for n-type.
Yeah, so this is a p-type semiconductor, this is an n-type region. Okay, so for p-type we need to dope the semiconductor with a trivalent element. Okay, such as example is aluminium. So it accepts an electron, it is deficient in one electron. Okay, say semiconductor, silicon, germanium, all these have 4 electrons in its valence band. So now this is trivalent electron, it needs to accept an electron. So this accepts an electron, and what happens is that the electrons which leaves the whole host material, now what will happen? It will leave behind a hole behind. So if you have this as a host material and you give a trivalent element over here, okay, say this is a trivalent element. Now it has one less electron. Okay, so what will happen? It will take one electron from the host, so it will leave behind a hole, leaves behind a hole. And now what will happen? It leaves behind a hole, it itself will become negatively charged. Okay, so it is an acceptor electron, it accepts I'm sorry, so I would say these are acceptor ions. Okay, it becomes an acceptor ions, that is, it accepts one electron from the host material. Okay, and similarly for n-type, you said pentavalent, so it will donate one electron. Okay, n-type is pentavalent, it donates one electron to the host material because it is having one extra electron. So this is n-type, this is p-type. So when you join these two, so there is a gradient in the carrier density, excess of holes over here, excess of electrons in this region. So there will be a what will happen when you have a gradient? Suppose, what will happen when you have a gradient? Can someone tell me? What will happen when you...
Movement of charges.
Yes.
Movement of holes, electrons.
So there is a concentration gradient of charges. So if there are more of holes over here, more of electrons over here, so electrons from here will move from lower concentration to higher concentration. Holes from here will move from n-type to p-type. So in this movement, what it does, it leaves behind the what does it leave behind? It will leave behind the negative ions and the positive ions. If electrons are going from here to here, it will leave behind the positive ions, and holes are going from here to here, it will leave behind negative ions. So what happens? A region will be formed which will be depleted of all what? Depleted of moving charges. This is a depletion region. So this region is depleted of, moving charges. So that's why we call it a depletion region. So this is a whole structure of a semiconductor diode and how it is formed. Okay, so now tell me, what if I have, this is my depletion region, this is my p type, this is my n type. So now suppose I bias it in such a manner that the p type is connected to the positive terminal of the battery and the n type is connected to the negative terminal of the battery. What is going to happen? What will happen? I hope you understand the mechanism of a diode. There are two terminals. I'm connecting the p type to the positive and the n type to the negative. What is going to happen over here? I'm giving it a bias. Can someone answer? It's an easy question.
Width of the depletion layer going to change.
And why is that going to happen? Why will width of the depletion region change?
Because we are giving external source.
So what happens? Why will depletion region deplete? I mean, the depletion region width will decrease. Why? What is the external source doing over here? The external source must be doing something. What is it doing? So basically what is happening, I'm giving some bias. Okay, so there is electric field develop over here, as you say, until an equilibrium. Electric field is from positive to negative. Now here I am giving another electric field. Okay, so they are countering each other. Okay, so what is happening? This is positive, it is repelling the holes from here to here. This is negative, it is repelling the electrons from here to here. Okay, so in the process, what is it going? Both these holes and electrons, they will neutralize in the depletion region, and the depletion region is gonna, what will happen to the depletion region? It will decrease. This is the whole mechanism. That's why it's decreasing, because of the movement of the holes and electrons towards the depletion region, and then joining over there, okay, with their respective charges. All right. Okay. Next question. Which of the following band gap diagram, I should say, band gap diagram, this is a band gap diagram, actually it's an EK diagram, is suitable for use in light sources?
Ma'am, first one is direct band gap and second one is indirect band gap.
Yeah, this is a direct band gap, but my question is something different. You just told me what kind of band gap. This is an indirect band gap. So I want to ask the question that which one is suitable for use in light sources?
Ma'am, direct band gap. First one.
Okay. So the answer to this is, I'm sorry. The answer to this is a direct band gap, which is the first diagram. Okay, suppose this is diagram 1, this is diagram 2, so first diagram. Now my next question, why?
Ma'am, because it is easy to, the electron goes to the conduction band. And
How is
then
it easy?
he came to the valence band, then there is some release of photons.
I cannot hear you properly. Can you please write it down? Why is it easy? Can you please write it down? I was not able to hear you properly. Why is it easy over here? See, whenever there is a transition from a valence band to a conduction band, there is need for the conservation of what? What should be conserved? Energy and momentum. Okay, so this is an EK diagram, energy with momentum diagram. Here, the minima of the valence band is, maximum of the valence band is directly above, below the minima of the conduction band. So this is my conduction band, and this is my valence band. Okay, this is my conduction band and this is my valence band, and we see that over here what is happening, since this is a direct band gap, so directly the electrons are getting transferred from the valence band to the conduction band. There is no loss of energy over here. Okay, so there is no loss of energy, and we need to conserve both momentum and the energy, and also there is no loss of momentum over here. Okay, but what happening is that for the conservation of energy, we need to, there's this band gap over here. So for the conservation of energy conservation is easily satisfied over here whenever it is going from here to here. Energy conservation will be satisfied. But what about momentum? Momentum also needs to be conserved, right? So it will travel this extra space, in space, extra length. It has to go over here, and then it will get, and then it gets transferred to the conduction band. So there is, this is quite difficult in this case. Momentum is not conserved. So to conserve momentum, it has to travel this thing. So that is why the direct band gap direct band gap materials are suitable for using in light sources, used as a light sources. So what happens in a LED is that when an electron is in the what shall I say, valence band, conduction band, yeah, light emitting diode. So when an electron is in a conduction band, it comes back and recombines with the hole, and in the process what it does, it emits a photon. Photon is emitted. Okay, photon emission takes place when after recombination. So for an LED, for the purpose of using a diode as an LED, we need to ensure that there is maximum of electron hole recombination. We'll see that how we are doing it. Okay, so let's move on to our next question. So let's see what's our next question is all about. So here I've given few, I've taken this from an internet, and there are few differences between the valence band, indirect and the direct band gap semiconductor, and I've given examples about that. So I would like you people to go through this and let me know if you have any questions in any of these points. I will try to clear it. So as I was saying, that a very important point is that the recombination, I said that we should have maximum recombination of electron and hole. But these recombination are again of two types: radiative recombination and non-radiative recombination. That is, recombination leading to the emission of photon, that is known as a radiative recombination, and recombination which does not lead to any emission of photon is known as the non-radiative recombination. Okay, so it's very important for diode to work as an LED that we have more of radiative recombination. Okay, Examples of a direct band gap, which can be used as an LED or as a light source in a laser, is gallium arsenide. And examples of indirect band gap semiconductors are silicon and germanium. But silicon and germanium can be also used as a photodiode. Okay, and one more thing about diodes I would like to emphasize is an important part which I didn't tell you, that the current, if I bias the diode, there is a flow of current in it, and that current is exponentially proportional to the voltage applied. So if I want to draw a current versus voltage diagram, so this is my voltage, this is my current. So initially when the voltage is low, the current developed will be very small. Okay, but as and when we keep on increasing the voltage, after certain threshold of the device like silicon or
Excuse
germanium.
me, ma'am. You are not.
Huh?
Your slides are not moving.
Sorry,
Your slides are not moving.
I'm not moving the slide, I'm drawing something.
I didn't see any drawing on this. You just
Okay,
you just underline examples. I think.
I understand. Okay, what about is
Oh,
proportional to exponential v? Can you
I am
see
not
that?
able to see.
Sajdeen, can you see that?
Yes, ma'am.
Thamis, maybe you can just try to see a different connection. Okay,
Okay.
I'm writing something else. Diode. Can you see
Now,
this?
yes, ma'am. I can now see.
Okay,
Now,
fine. So what I was saying is that as and when we keep on increasing the voltage applied or the bias which is applied to a diode, there's increase in the current. But these diodes have certain threshold voltage, that is the minimum amount of voltage that should be imparted to a diode, given to a diode, so that the current increases to a greater extent. So as and when the bias is increasing beyond the threshold voltage, there is an exponential rise in the current. Okay, there will be an E and then there will be an exponential rise in the current. But we can also give a reverse bias. This is what is called a forward bias. Okay, we can also give a reverse bias, that is negative to the positive, where N is connected to the positive and P is connected to the negative. N positive, P is connected to negative, and this is what you call reverse bias. So in this, there will be very small current, but at some point there will be a, what you say, a avalanche, or you say there will be a saturation of the current at some voltage. Okay, there are different diodes available when it is operated in a reverse bias region. So this is known as the reverse region, reverse bias. Okay, so all the light sources are used in this region, and all the detectors, photo detectors specifically, are used in this region. Okay, I hope you know about this, and you must be clear how is it done. So we are now all set to use my diode as a light source. We learned about the basics of a diode, that is, it is made of a semiconductor material. We dope it, increase the carrier density, but we have to choose a diode very nicely such that there is an overlap in the sense the band gap is a direct band gap semiconductor, and there is maximum of radiative recombination of the electrons and holes, and it is operated in a forward bias. Now let us move on to an example of an LED, of a semiconductor LED used as a diode. So there we need to understand few terms and the mechanism of how LED works as a light source. LED is basically light emitting diode. So LED is a device. It converts electrical energy to optical energy. Okay, all right, you understand this? So we can impart electrical energy to my device to that it responds and reacts, and there is the electron stays in the conduction band for some time, then it comes back to the valence band, recombines with the hole, and in the process emits a photon. Okay, so the question is, in an indium gallium arsenide LED emitting at a peak wavelength of 1.68 micrometers, and there is a drive current of 40 milliamperes. So it has an internal quantum efficiency of 60%, and there is a radiative recombination lifetime in the active region whose refractive index is given 3.5, and the radiative recombination lifetime is 60 nanoseconds. So my first question is, what will be the total carrier recombination lifetime? So recombination lifetime are of two types. Okay, this is non-radiative recombination lifetime. Okay, and there is another thing which is radiative recombination lifetime. That is radiative recombination lifetime. Okay, so the total recombination lifetime, tau total, will be given by 1 by tau total is equal to 1 by tau nr plus 1 by tau r. So this will be tau total equal to tau r times tau nr. I'm sorry, I need to use an eraser. Tau r times tau nr divided by tau nr plus tau r. So this will be the total lifetime. But I have to relate this total lifetime to something, to the information given here. There's something called internal quantum efficiency. What do you understand by an internal quantum efficiency? So, what happened? Internal quantum efficiency is basically a ratio. So all the electrical energy that we provide to my diode won't be converted to optical energy, right? So there will be a part of the electrical energy that gets converted to optical energy. So I hope you understand these terms, the physical meaning of that. Is it clear, or shall I keep it more clear? Thamis and Sajin, did you understand the meaning of internal quantum efficiency?
Yes, ma'am, I can.
Yeah, what about Sajin? Sajin? Okay. Alright. So basically, internal quantum efficiency is the ratio of the total radiative emission rate divided by the radiative emission rate. How much rate is the, at what rate is there is a radiative recombination, and that is resulting into emission of photon. So that is total radiative emission rate to the overall rate. Overall rate at which the carriers in the sense the holes and the electrons, these carriers recombine. Okay, so total radiative emission rate. So when I say radiative emission rate, that means that from the conduction band to the valence band, the electrons drop down, recombines with holes, and there is an emission of photon. So this has to be at some rate, right? In some time, and how much time, whether in how much time this is happening, what is the lifetime of this. Okay, so this radiative emission rate will be inversely proportional to the lifetime. Okay, lesser the lifetime, more will be the radiative emission rate. More the lifetime, less will be the emission of this. Okay, because the electrons will stay there for a longer time, stay in the conduction band for a longer time. If the lifetime is more, lifetime of this electron in the conduction band is more. And also same thing goes for the non-radiative. So this is radiative emission rate, and for the non-radiative again, tau nr. Okay, the same thing is happening proportional to the non-radiate. I'm messing up with all the formulas. Sorry, messing up with the notations. Tau r. So if the number of carriers, if n is the number of carriers, okay, so r, that is the radiative rate, will be equal to n by tau r. Tau r is the lifetime of the radiative emission, and tau nr is proportional to n by tau nr. This is for the non-radiative case. Okay, so this is my eta end. So if I write eta end, I said total radiative emission rate, this will be this, by overall rate. Overall rate will be the sum of the radiative emission rate plus the non-radiative emission. That will be the overall rate in which the carriers recombine. So this will be equivalent to 1 by 1 plus RNR by R, this thing. So what will be this equivalent to? This will be equivalent to, can you answer? 1 by 1 plus, this will be tau r. Tau r, no? And
Tau
are
r.
they are tau r by
Tau
tau
nr.
nr. Right. Okay. So now we know that tau total is tau nr times tau r by, I have written this. Okay. So here I can just substitute. Okay. Just do the math and you can just simply substitute. This will be simply tau total by tau r. I hope you understand this. You do the maths, you'll get it. Okay. So eta int times tau r will give you the total carrier lifetime, and that is simply, how much is that? This is 0.6 and the radiative recombination rate is 16 nanoseconds. So if you want the answer in nanoseconds, you just multiply 60 by 60 times 0.6. That will be given, that will give you the answer of 36 nanoseconds. I hope this is clear. I hope the concept also got clear of radiative and non-radiative recombination and the related lifetimes and the rate. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yeah, good. Okay, now I have this device. It is operating at some temperature, and this temperature is 40 degrees centigrade. What is the full width half maximum? So what is full width half maximum?
1.8 kBT divided by H.
Correct. So basically, if I draw this graph of say frequency, excuse me, student, please. So if I draw this graph, say with the terms of energy, and this is some rate of my emission. So I'll have this over here. So this is my full width half maxima. Okay, full width half maxima, and this is given by 1.8 kBT by H. Okay, so it's actually the maximum intensity divided by what? Root 2, and both sides you'll see where it coincides. That will give you the full width half maxima. Yeah, so this is your answer, that is 1.8 kBT by H. You need to convert, the temperature was given in degree centigrade. Okay, so in Kelvin, this temperature in So in Kelvin, what will be this temperature? This temperature in Kelvin will be given by 40 plus 273, which is given over here by H. Okay, by H. Yeah, by H. So that is given by this. So this is the spread. The spread in the frequency. Okay. Now let's move on to the next question. The next question says, we know the forward current. Okay, that is given. Cool. Forward current is 2.7. The forward current is 20 milliamperes. Okay, then it is operating at some voltage, which is 2 volt. And temperature is room temperature. Room temperature means 300 Kelvin. I'm also given information of the internal quantum efficiency and how much is the carrier lifetime. That is about 1.25 nanoseconds. And the refractive index of my diode is 2.7. So what is the question? The internal photon flux for the given energy. What do you mean by internal photon flux? This whole term, very difficult term. Internal photon flux. What is the meaning of this? Please answer. Photon flux, like number of photons, something. Photon, how many number of photons are generated? So as I said that not all the recombination of electrons and holes will give rise to emission of the photons. Okay, so that's how we define internal quantum efficiency, right? How much electrical energy is converted to optical energy. That is how many photons are being generated. So internal photon flux is basically about that only. How much fraction of photons are being generated. So you give some electron. So basically we are giving electrical energy. That is, electron goes into the diode. Electron goes into the diode and photon comes out, right? And photon comes out. So this is suppose my black box. Here I am giving some electrical energy, that is I am giving electron, and here there is a photon emission. This is my diode, say. So electron goes in, photon is coming out. So electrical energy getting converted to optical energy. But how much fraction of this electron is getting converted to a photon? How many photons are generated per what? Per electron, sir. Okay. So fraction of the injected electrons. Basically, we inject few electrons in my diode. So what fraction of the injected electrons is getting converted to a photon flux? So this is my photon flux, meaning fraction of injected electrons. Now here I'll say some unit, say electrons per second. How many electrons you are injecting per second, and how much of that is getting converted to a photon flux. How many photons are being generated per second per unit area? So that photon flux, how many electrical current is converted into photon? So that photon flux, internal photon flux, it will be given by this formula. Internal photon flux is how much current is there by the electron times the internal quantum efficiency. Because internal quantum efficiency tells about the ratio of the recombination rate to the overall recombination rate. Ratio of the radiative recombination rate to the overall recombination rate. So internal quantum efficiency gives us information that if internal quantum efficiency is 60% or 70%, that is 70% of the electrical energy is converted into optical energy. 70% of photons are being generated. Okay, so that's how it's given. So this is number of electrons per second, and this is how many electrons are getting converted into your photons. Okay, so this gives information about this, and this is number of electrons per second. If you multiply them, then you'll get the photon flux, how much photon flux are being generated per second for electrons injected per second. Okay, so I will ask you to cross check this value. So the current is 20 milliamperes by the electronic charge 10 to the power minus 19, and how much was the internal quantum efficiency? That was 60%. Okay, into 0.6, 60 by 100, that is 0.6. So you can do the math and just let me know whether you get the same answer as this. Just check with the answer. Okay, find the modulation bandwidth. Find the modulation bandwidth of an indium gallium arsenide phosphate LED if the carrier lifetime is 5 nanoseconds. What is the meaning of modulation bandwidth? Please answer. What is the meaning of modulation bandwidth? What is the meaning of modulation bandwidth? Like, if I want to ask physically, how do you explain this term? This is just a term. Modulation bandwidth. How do you physically explain this? Tamis? Sajdeen?
I have no idea.
Have you read about this in the course? Sir has taught about this. Tamis? It's related to frequency. Tamis, can you answer please? It's related to frequency. I hope you will be able to answer. What is modulation bandwidth?
Forgot. I'm not able to answer.
Huh?
I remembering the answer, but I'm not able to express it.
You can say it. You can say it. Whatever is coming to your mind, you can say that. What is modulation bandwidth? Shall I give this to you as a homework?
Yes, ma'am.
Okay, you'll find the answer and let me know in the next class. It's there in Sir's lecture. Okay, I'll give this to you as an homework. So basically, it tells it about the frequency response of an LED, how the LED responds to certain frequencies. So what shall I say? Basically, it depends on the carrier dynamics. Okay. So the electrons and holes, they are moving, and there are certain lifetime associated with the carriers, that is going from a conduction band to a valence band, and so lifetime. Okay, so it's related to that. I can give you this hint. Okay, so basically it depends on the lifetime. As I said, carrier, it depends on the carrier's lifetime, and also what is the frequency response of this. Now all I want you to do is to explain this to me physically. If these are just terms, carrier lifetime, modulation bandwidth, physically what it means, physical meaning of modulation bandwidth. I'm giving this to you as a homework. Please come back with an answer, or you want you can write in the chat also. Modulation frequency, I'm writing. No, modulation bandwidth. Okay, what is modulation bandwidth? Okay, so you have to answer this question. Now let's move on to next question. Next question is pretty simple. I hope you'll be able to answer this. I want you guys to give it a try. Can you answer this question? So basically, when we try to make a diode, like this is a compound diode. Okay, this is a compound diode. So certain percentage of it added. Okay, so doping, as I said, doping is of some percentage. So y percentage of arsenic, x percentage of gallium, 1 minus x percentage of indium, and 1 minus y percentage of phosphorus. So we have been given that x by y ratio is this, and my x percentage, how much we are doping it with, or how much of this material we are adding, that is given. And you have to find the operating wavelength of a semiconductor, and I'm given the energy expression. Like if we make a semiconductor by such method, like 1 by x part of indium and x part of gallium, y part of arsenic, and 1 minus y part of phosphorus, then the energy band gap would be given by this. This would be the expression of the energy band gap. You are asked to find about this will be y square, okay, not y2. You are asked to find the operating wavelength. Now here, what do you mean by operating wavelength? What do you mean by operating wavelength over here? Okay, I'll tell you. Operating wavelength means uh, what wavelength will correspond to this energy gap. That is the meaning. I told you the answer over here. That is the meaning of an operating wavelength. So if I have my diode, this is my energy band gap Eg, this is the conduction band, this is the valence band, and if there is a recombination of carriers, then there is emission of photon. So this photon will have an energy which will be equivalent to the band gap of this material. So this hc by lambda, I'm saying E of lambda, hc by lambda will be equal to Eg. So this lambda is known as the operating wavelength. Okay? Did you understand? It's clear. So here my job would be to find how much this energy is, and to find this energy we need to find y. How will we find y? We will find it from this ratio. X is given, okay, x is given, so x by y is equal to 1 by 2.2. We can find out y. Whatever y we got, we'll substitute in this expression, and then we'll just equate it to hc by lambda. So let's see. Y is equal to 0.88 and x is equal to this. Okay, so Eg will be equal, Eg is given, that is equal to this. Substitute y, you got this in electron volts, and now simply just substitute this. So lambda is equal to 1.24 by Eg. Okay, so this would be around the operating wavelength, and we give some range of the answers. Cool? Simple and easy?
Yes, ma'am.
I hope it's understandable. You're not just doing it mechanically, you're understanding the process and the logic behind it, right? Is it quite logical? Is it making sense? Okay, yes, ma'am. Alright. Okay. What is my next question all about? Oh, this is a simple question. We are given all the information that is required. We have given the length of my laser. L is equal to 0.3 mm. Okay. Refractive index. N is given 3.4. It has an internal loss. Alpha int is equal to 0.4 per centimeter. Emitting a 150 nanometer wavelength. Lambda 1550 nanometers. R1 100%, R2 80%. Longitudinal mode spacing, free spectral range in terahertz of the LED. This is very simple. We had done it since the past two classes. What what do you mean by this? The spacing between two modes, right? In an LED, in a laser, there is oscillation. This is my laser. My light is going, but there is an oscillation of this, so that there will be an amplification. So this leads to presence of static waves, and so few frequencies only sustain or survive in the resonator. Okay, standing waves are there, only few modes will survive in the resonator, and that criteria is given by constructive interference. Okay, so from there we find which frequencies will survive. Okay, and from here, if we subtract delta nu, what will be delta nu? C by 2n lambda. Which frequencies will survive? MC by 2n L. Okay, clear? So simply you just substitute and get the answer. C by 2n lambda. Sorry, C by 2n L. So just convert it. If in terahertz they're asking you, convert the gigahertz into terahertz. Okay.
Ma'am, what about the other values that alpha int and
So is
lambda?
that required over here?
No, ma'am, it is not required.
Okay. Chalo. Let's move on. My LED is designed to have the corresponding wavelength. Okay. My LED is designed to have this corresponding wavelength. Lambda is 1.31 nanometers, has the following parameters. Internal quantum efficiency is given 0.5, refractive index 3.5, injection current. So this is actually IT. What is IT over here? Injection current, which is helping us to achieve threshold, the threshold at which my releasing will start, and it is biased at a current. The current, biasing current, is milliamperes. What will be the output power? Do you know the formula for output power? Okay, I'll tell you. P output is basically how much power is output. You have something called external quantum efficiency, which is dependent on the refractive index. We have talked about internal quantum efficiency, how much of it is converted to, like, how much electrical energy is converted to optical energy, and there is this current value. Okay, the current would be the whatever bias current you provide minus subtract the whatever threshold current is there, that is how much current is required to achieve the lasing threshold, and then you have what should be the energy of the photon which is emitted, and that is given by h nu, and that you can convert to 1.24 by lambda 0. Basically this one should be I by E, so that goes over here in this h nu into I by E. Okay, times the internal quantum efficiency will give you the internal power. If you want the output power again you have to multiply that with the external quantum efficiency, and external quantum efficiency is dependent on the refractive index of the material. Yeah. So I've told you like how to find out the output power dependent on the internal quantum efficiency, external quantum efficiency, how much current is getting used up in this, and how much energy of photon is being emitted. Okay, so that's how you find the output power. Now let's move on to the next question. This is an interesting question. I will leave it to you guys to match this following. Silicon goes to which characteristic? Absorption and emission. Where will silicon go? Absorption in visible or absorption in near IR? Okay, let's do with the easier one. Indium gallium arsenide phosphate. These are all used in LED. Emission in near UV and visible or emission in near IR? Okay, so
Ma'am, 1.14.
Okay. So germanium has more energy than silicon. So the absorption will be in a lower wavelength range or a higher wavelength range. Okay, I'll tell you the answer. So A goes to 2, B is 4, C is 1, D is 3. A is 2. There will be absorption in the visible region. B is 4. Indium gallium arsenide phosphide. It will be in IR region. And then indium gallium nitride will go in this. For this, you need to know the band gap values of these things. And germanium will go in absorption in near IR. Okay. I hope it's all clear. Just go through what are the band gap values of silicon and germanium and indium gallium arsenide. You'll get your answers. Okay. So this is the next question. It's an easy question. In an aluminium doped silicon material, the Fermi energy level appears to be closer in conduction band. Okay, and the aluminium dopants in silicon accept electrons and increase the concentration of holes in the valence band. What will be the answer? This is the Fermi energy. A is false, but R is true. Alright. So basically, what happens? Fermi energy is the level below which all levels are completely filled, above which all levels are completely empty. Valence band. So in an intrinsic semiconductor, the Fermi energy lies in between conduction band and valence band. But when you add dopants, okay, this level will move up and down. So when you add electrons, the Fermi energy will be closer to the conduction band. It will move up and up. And when you add more holes, the Fermi energy will be closer to the valence band. This is the Fermi energy. And since this is an aluminium doped silicon, that means it's a p-type material. And for p-type material, the Fermi energy is closer to the valence band. Okay. And aluminium dopants, yeah, R is true. Aluminium dopant, it has 3. It is trivalent. Aluminium is trivalent, 3 plus. So it will accept electrons and it will increase the concentration of holes in the valence band. So A is false, but R is true. Okay. This is the answer. Now next question is about the slope efficiency of a diode. Slope efficiency means the output power per unit watt. The current. Okay, that's the slope efficiency. Like when you plot the output power to current, you find the slope of that. So that is the slope efficiency. So of that, LED is negative at high current levels because of a phenomena called droop. Remember, sir had drawn this diagram. There was a droop. What is this diagram? What will be the y-axis and what will be the x-axis in this? Why droop? This is, as I said, output power with current. So here is the droop. I think some power fluctuations are happening in my place. Okay. And at high drive current levels, increase Auger recombination. I want you guys to find the meaning of Auger recombination. That is a non-radiative in nature. Is observed in LED due to high temperature buildup. I have given the answer that both A and R are true, and R is the correct explanation of A. But I want you guys to connect these two. How is slope efficiency related to this? Just find out an answer. Like, think on it. Okay. Next class I'll tell you this answer. Just remind me to tell you about this answer. Okay. How is A related to reason? Okay. Okay, so we'll meet next class, and thank you. Next class we'll be doing light photo detectors. Okay. So thank you, class. Thank you for your attention.
Excuse me,
And
ma'am.
yes,
Ma'am, can you please share the PPT also in the portal, if
that has
possible?
been that has been shared, I think, right?
Ma'am, actually,